Howdy everyone, welcome back for Chapter 9, Molecular Geometry and Bonding Theories. It's a fun chapter where there's not a lot of math because we're skipping all the math in it. There's actually not a lot of math in the chapter, but for how we get the answers that we're going to get here, oh yeah, there's a lot of math. So we're going to go through and see what we can get with just the more descriptive approach. So if we go here, the main thing in this chapter is talking about molecular shapes. What does the three-dimensional shape of the molecule actually look like? So Lewis structures that we drew in Chapter 8, well, they tell us what's bonded together. They tell us if it's a single bond, double bond, triple bond. They tell us that there's non-bonding lone pairs, but they don't tell us shape, at least not by themselves. But we're going to use those Lewis structures to get those shapes because we can see some common shapes that molecules take here. We have linear, we have bent, we have trigonal planar, trigonal pyramidal, T-shape, we have tetrahedral, octahedral. There's a whole bunch, and we get those shapes because of the Lewis structure. So that's why we have to make sure we have that stuff from Chapter 8 down. We're going to be using it all the time here in Chapter 9. All right, so what's going to tell us the shape? We need the bond angles, right? What is the angle between any three atoms? The basic idea that we're going to use is something called VSEPR. Which is a model. It is not what's really happening, but it's what we call a heuristic. It's a really simple assumption that we can do to say, okay, if I follow these simple rules, I'll get very, very close to the right answer for very little brain power and time. So yeah, we're going to do that. All right. So with VSEPR, we can use it to say, well, what's our simple rule? And the simple rule is electron pairs, since they're all negative, electrons are negative, they're going to repel each other. And they're going to try to move as far apart as possible in 3 dimensions. And that moving the electrons as far apart in 3 dimensions will tell us the overall shape. All right? Now, how do we figure that out? We figure out how many electron domains there are. And so an electron domain is anywhere, any region of space, where we've got electrons spending time. So it could be a bond, like this single bond here. It could be any other bond, like a double bond. That's a single region of space. Here's a single region of space. Oh, and here's a non-bonding pair. That's a region of space. So in this molecule, even though a lot of the things are different from each other, we'd say it has 4 electron domains because it has 4 different spots that electrons are spending time. So that's what we figure out first. That's why we have to have the Lewis structure. We need to be able to look at it and say 1, 2, 3, 4 spots. Right? From that, we're going to say, okay, the best arrangement is the arrangement that spreads them out as much as possible. They give the analogy here of balloons. How do you keep 2 balloons farthest apart? Put them opposite each other. How do you get 3 balloons far apart? Make a triangle. How do you get 4 balloons apart? Make a tetrahedral. I like to use the analogy of when strangers are in an elevator together, right? They will naturally spread out, and then if someone else joins in, people kind of rearrange to spread out some more because you're in an elevator with strangers. You don't want to get too close to them. All right? Oops. The next thing, it's a table from the book. You just have to memorize it. You do have to memorize the bond angles. You have to memorize the shapes. You just simply have to. And these shapes are what we call the electron domain geometries. Sometimes it's called the electronic geometry. But it's just saying if we're only looking at how many electron domains we have or regions of electron density, that's where it's going to tell us this is your basic shape for the electrons. So we have to memorize this table. If there's 2 domains, it's linear. If it's 3 domains, it's trigonal planar. Linear was 180, trigonal planar is 120. If there's 4 domains, they spread out in 109.5 degrees. We call that tetrahedral. If there's 5 domains, we call it trigonal bipyramidal. You can kind of see the framework. There's a triangle in the middle, and then there's an up and a down for 2 pyramid sort of things. And then if there's 6 domains, we call it octahedral. Everything's 90 degrees. It's more of a square base, and then you have 1 up and 1 down for 2 pyramids there. The number of electron domains, as they say, is sometimes called the coordination number, saying like how many connections is that atom making. All right, so you have to memorize table 9.1 in the book. You got to memorize these names. You got to memorize these bond angles. All right. As we move forward then, we're saying, okay, well, that's the electronic geometry, what all the electrons are doing. We want to know about the molecule, though. When we just look at the atoms that are connected, what's the shape we get there? And so the molecular geometry comes from the electron domain geometry. So we have to draw the Lewis structure first. We have to get that electronic geometry second. And then we say, well, what are the bonded atoms doing? If we look only at the bonds, what shape are they in? And that gives us the molecular geometry. So tables 9.2 and 9.3 give us all the ones. We're going to walk through them. But again, those tables you must also memorize. What are the shapes that come from those electronic geometries when we have fewer and fewer bonds? All right, so the most basic one is linear, which no matter what, if it's electron domain linear, it's molecular linear. Whether it's one set, two atoms together or a set of three together, it's got to be linear. All right, so linear, pretty easy. With trigonal planar, there are two molecular geometries. If everything's a bond, it's trigonal planar, and that's a pattern you'll notice in the other ones. If every domain is a bond, then the molecular geometry will have the same name as the electron domain geometry. So trigonal planar with three bonds, trigonal planar. But if it's two bonds and one non-bonding pair, then because it just goes up and back down, we call it bent, right? The bonds bend, so the whole molecule is bent. All right. For tetrahedral, there's going to be three possible molecular geometries. Could be tetrahedral if everything's bonding. We could have trigonal pyramidal, or we could have bent. So let's look at those. A little bit easier here to see. So everything's tetrahedral. There's four things around the central atom. If all four are bonds, still tetrahedral, just like methane here. If three of them are bonds and one is a non-bonding pair, we call it trigonal pyramidal because these three are still going up to the center, but then we pretend we can't see that, so it looks like a pyramid. So ammonia here is a good example of that. And then if two of them are bonds, but two of them are non-bonding pairs, then we call it bent again, so that, hey, it's bent like water here, because those bonds are about 109.5 degrees apart again. So notice bent was here in tetrahedral. There's also the bent from trigonal planar, but the bond angles for those two different versions of bent, not the exact same, so double check. It all comes from the electron domain geometry for what the approximate angle will be. All right. Now, one part of VSEPR that we say, and this isn't strictly true, it's more of, again, a simplification to help us come up with the right answer without thinking too hard about it. We say that the non-bonding pairs are larger than bonding pairs, that they take up more space. And because they take up more space, they start to squeeze the other bonds closer together. So methane, because everything's a bond, is about 109.5. Because ammonia has this one non-bonding pair, we say, oh, it squeezes the others close together, and now they're only 107. And then we say, oh, water has two non-bonding pairs. They squeeze things together more. So now instead of 109.5, it's only 104.5. This is a total lie. This is not what actually happens. But for the level of this course, this is our basic model explanation of what happens, so we're going to leave it there. Like I said, it's not really what goes on, but I mean, give it a couple more years of chemistry courses, and then we'll get to the right answer. All right. Multiple bonds, same thing here. Again, not what really happens, but we say it happens. We say that double and triple bonds, because there's more electrons in that area, double bond would have 4, triple bond would have 6. Well, they have more repulsion. They, again, squeeze the other bonds further. So this is called phosgene. It's a carbon with a double bond to oxygen and then 2 single bonds to chlorine. That's a trigonal planar shape, so it should be about 120 degrees. But we say, oh, the double bond takes up more space. It squeezes these chlorines back, so their angle gets less than 120, while these other two angles get greater than 120. Again, this is not what's really happening all the time, but it's a simple explanation that gets us close to the right answer. All right. If we have those Lewis structures that broke the octet rule, that had more than an octet, they had 10 or 12 electrons, we have shapes for those too, and we'll look at them here. This is table 9.3 in the book. You must also memorize these. So the first one, if there's 5 things around the central atom, we call it trigonal bipyramidal because there's a triangle in the middle. And then we can make 2 pyramids, one going up and one going down. These ones that are going around the center in the equilateral triangle, we call them the equatorial positions. The one that's going up and down, we call them the axial, like they're the axis. You can imagine this one spinning it like a top. The axial are the top and bottom that wouldn't look like they're moving, and then these 3 around the center, well, they'd spin really fast and they'd look like an equator. Right? If you get to use model kits, you can make this, and then yes, you can actually spin it like a top, and it works really well to demonstrate this. All right. Well, we can get 4 molecular geometries from trigonal bipyramidal. So if we look at that, again, if everything's a bond, it's trigonal bipyramidal. If one of them is a non-bonding pair, it is always at an equatorial position. And we call the remaining shape a seesaw shape, because if you imagine leaning it down on these 2 equatorial, well, then the actual ones, it's like a seesaw going back and forth. And again, with model kits, you do that, and you have way too much fun with a seesaw. If there's 3 bonds and 2 non-bonding domains, again, both non-bonding go in the equatorial. So what's left is T-shaped, just rotate it 90 degrees. If only 2 things are bonds and you have 3 non-bonding pairs, again, all 3 non-bonding go equatorial. You're only left with an axial and another axial. Well, hey, that's a straight line, so we call it linear. So make sure you know those molecular geometries coming from trigonal bipyramidal. And then the final one is the octahedral. This is when there's 6 electron domains around that central atom. So we get 3 shapes here. There could be more, but there's only 3 that they make you learn. Octahedral, so if it's all 6 bonding, it's octahedral. If there's just 1 non-bonding domain, not sure why that X is there, then we just remove any one, because you can just rotate the thing around, it's always 1. We call it square pyramidal, because you have a square, and then one thing sticking up to make the cap of your pyramid. And then the one to remember, if it's 4 bonds and 2 non-bonding pairs, well, the non-bondings are always opposite each other, so we call this resulting shape square planar. It makes a square, and they're all flat, square planar. All right, so all those shapes, I know it seems like a lot, but a lot of them, the name kind of makes pretty good sense of where it's coming from. So that's what we're looking for to tell us what is the molecular geometry from the electron domain geometry. All right. Now, what about larger molecules? What if it's not just one atom in the middle and then everything else around it? Well, then we just look one atom at a time. So here's a molecule. This is acetic acid. It's vinegar. So we'd say, oh, around this carbon, well, it has 4 bonds around it and no lone pairs. So both the electron domain geometry, that's tetrahedral, and the molecular geometry is tetrahedral. All right. If we move to say, well, what about this carbon in the middle? Well, there's 3 electron domains around it, so that's trigonal planar, and all 3 are bonding, so trigonal planar. But then we get to this oxygen. Okay, there's actually 4 things around it because there's 2 lone pairs not pictured, so that's a tetrahedral electron domain geometry. But because only 2 of them are bonds, well, that's a bent molecular geometry around the oxygen. So with big molecules, you just say, well, what is it for this one? What is it for that one? Just one at a time, follow the same rules. All right. The last thing we'll do in this section is the molecule overall polar? In Chapter 8, we talked about polar bonds. But that doesn't always tell us, will the molecule be polar? Because we have to see, well, how do all those polar bonds line up with each other? And so we're going to ask, is it covalent or ionic? If it's ionic, we don't talk about polarity. We just say, oh, no, it's ionic. There are ions. There are charges. But if it's covalent here, we say, first off, are the bonds polar? Do they have a dipole like we learned in Chapter 8 with the electronegativity difference? If they're not polar bonds, and none of them are, well then right then and there, the nonpolar molecule. It can't be polar if there's no polar bonds. But if there are, we have to check. So they say here, does the average positions of our partial plus and partial minus coincide? Meaning, does the overall dipole moment equal 0? I'm going to rephrase that. Do the polar bonds cancel out? If they do cancel out, then it's nonpolar. It's like a tug of war between identical twins. No one wins, so nothing's polar overall. Right? But if something doesn't cancel out, then yes, it is polar. And so for this one, say, well, how do we know if nothing cancels out? You are looking for any asymmetry in the molecule. If you have different atoms attached to the central atom, well, that'll be different polarity. They won't cancel out. If you have an atom on one spot and it's versus a non-bonding pair in another spot, well, those aren't the same thing. That's asymmetry. Doesn't cancel out. It's polar. All right, so you're looking for, does anything cancel out or not cancel out? The main thing is if you have all the same bonds and there's no lone pairs. So if our molecular geometry equals our electron domain geometry, so linear, trigonal planar, tetrahedral, octahedral, if it's the same, well, then everything's going to cancel out. It's going to be nonpolar. But as long as one thing is different, either from a different type of atom or something, there's some non-bonding pair instead of an atom bonded there, then it's not going to cancel out. It will be polar, assuming we have polar bonds. So if we look at some examples here, carbon dioxide, they're polar bonds, but it's a linear molecule, and it's equal and opposite. The one oxygen's pulling to the left, the other oxygen's pulling to the right. They cancel each other out. So even though there's a kind of a negative end, well, it's negative and negative, they cancel out. It's nonpolar overall. But with water, we have polar bonds, and hey, there's two H's, there's also two non-bonding pairs. And because hydrogen is not the same as a nonpolar, that's asymmetry. There's something different there. So yeah, here we get an overall dipole of negative at the top where the oxygen is, positive at the bottom where the hydrogen is. Doesn't cancel out. It's pointing up overall towards the negative, so that's polar. All right, so that's going to be the end of this video. I know it's a lot, but you got to be working on memorizing those tables.